Here we go with section 18.2, excuse me, potential difference. We've seen how the potential energy of a point charge in an electric field depends on the charge and the field and the distance, or maybe a better word than distance would be the location of that charge in the field. Now, a more useful concept in the study of electricity is called electric potential. Here's the definition of electric potential. Electric potential typically is called V for voltage, and it's equal to electric potential energy divided by the charge. The unit for electric potential is joules per coulomb. Think about that, energy per charge. And a joule per coulomb is called a volt, after Alessandro Volta, an Italian physicist. Anyway, electrical potential is the electrical potential energy associated with a charged particle divided by the charge of the particle. Now let's think about why this is a useful concept. I'm going to go back to my analogy, my gravity analogy, where I have a ceiling and a floor. And again, this is analogous to a uniform electric field created by parallel plates. In this scenario, my ceiling is my positively charged plate and my floor is my negatively charged plate. First of all, if I were to take a mass and put it anywhere in my room with the ceiling and the floor, it would experience the same force of gravity. No matter where I put it in the room, I would simply take the mass times g. Now g in this case is an indication of the strength of the field. What would happen if I took this this mass? What would happen if I took it to the moon? Would g be the same? No, it would not. G would change. Okay, now we learned about potential energy of a mass. Oops. Get rid of this for a second. We learned about the potential energy of a mass, and we learned that if you take a mass and you move it a certain height, like let's say I start here and I end up here, that change in height will determine the potential energy, or the change in potential energy of the mass. And it works the same way with charges. If I have a positively charged object, and if I were to lift that object in the field, or rather move it opposite the way it wants to go, so if I move it toward those positive charges, what I'm doing is I'm giving it electrical potential energy. And we've already talked about how that electrical potential energy is equal to QED. Now this is negative QED. This is very similar to MGH. You've got charge instead of mass. Our definition of field strength is this E, just like our definition of gravitational field strength is G, and then we've got a distance. So it really goes back to that definition of work. Now, what we want to do here is we want to come up with a way to define a potential energy change independent of mass or independent of the amount of charge. And so basically what we're going to do is we're going to focus on this part of the equation. You can imagine me dividing out Q, taking PE divided by Q. Okay, that's going to equal this new number called voltage, or potential difference. And what is this good for? Well, when we're working with electricity, we're not going to be working with just one charged object at a time. We're not going to work with just one electron, because we want to get to a point where we are working with current electricity. So when you look at an outlet, what an outlet does is it has a potential difference across the two prongs, the places where you put the plug. And what that does for you, what it does, first of all, in a household circuit, is it's usually about 120 volts. And it doesn't matter what appliance you plug in, right? You might plug in a hairdryer. You might plug in a toaster. You might plug in a light bulb. But my point is that all of them are going to draw different amounts of electricity. Ooh, actually, it would go that way, wouldn't it? They're going to draw different amounts of electrons, but what needs to happen, what needs to be constant, is the energy that each electron gets. And this idea of potential difference then gives us a sense of how much energy each electron gets. And that's going to be useful later when we determine how much power is consumed in current electricity. So right now, when you see this stuff, it seems very abstract, and it is abstract. But later, when we get to current electricity, this idea of voltage or this idea of electric potential will have a more specific meaning. And basically what it is it's two things. It's sort of the force that pushes the electrons through a circuit. And it's also going to equate to the energy that the charge holds. And then, of course, we dissipate that energy with our different appliances. Now, what about point charges? We've spent some time looking at uniform electric fields, but what about point charges? We can create potential energy with point charges. If you can imagine these two point charges and what would happen if you tried to push them closer together. We actually did this in the classroom with sticky tape, and we did it with the electrostatics stuff. You could feel those electrostatic forces. Well, it turns out that we can quantify the electrical potential energy that is stored when we push these two charges together, and it's just equal to K Q1 times Q2 over R. I'd like you to recall that Coulomb's law is K Q1 Q2 over R squared. So really what we're doing here is we're multiplying by a distance, and a force times a distance is equal to work, and work then is equal to this energy that is stored. Let's do a practice problem or two. The first one says, in the classical model, an electron has a radius of 2.82 times 10 to the negative 15th meters. Thus, two electrons could be as close as 2R. Calculate the electric potential energy for two electrons that are touching. Okay. Well, this certainly is the classical model, and the more we learn about subatomic particles, the more complicated it gets. But let's go with it, just for the sake of practice. First of all, the distance between the centers of the electrons is going to be 2 radii, so I hope that that makes sense. And we are going to calculate the electrical potential energy for those two. So I'm going to use the formula. Electrical potential energy equals K Q1 Q2 over R. K is 9 times 10 to the 9th. The charge on one electron is negative 1.6 times 10 to the negative 19th, but I've got two of them. And then the distance between them is going to be 2 times 2.82 times 10 to the negative 15th. And then I would get out my trusty calculator and compute that, and I would get 4.1 times 10 to the negative 14th. And that's joules, because it is electrical potential energy stored by pushing those two negatively charged objects close to each other. Let's look at another. What is the change in electrical potential energy of a proton as it moves a distance of 2 centimeters in the direction of a uniform electric field with a strength of 400 newtons per coulomb? Okay, so a couple of things that you want to do when you solve these problems. Whenever you see the word electric field, you want to ascertain whether you are working with a uniform electric field caused by parallel plates or an electric field caused by points. And this says uniform electric field, which means, again, that I am working with something, an electric field created by parallel plates. So I'm going to go ahead and sketch sort of a generic electric field, and I'm not just going to sketch the field itself. Here's the field. I'll make it red just for fun. I'm actually going to draw the plates to remind myself where that field comes from. You can't have a field without charge, just like you can't have a gravitational field without mass. Okay, so now they say that a proton moves a distance of 2 centimeters in this field. They're telling us that the strength of this field is 400 newtons per coulomb, and they're telling us that the distance that it travels is 0.02 meters. So first of all, I want you to think about this for a second. What happens when we allow this positive charge to move? It wants to move in the direction of the field, right? It wants to move to the right, which means it's going to lose potential energy. Just like if you drop an object in a gravitational field, it's going to lose potential energy. So I'm going to use the formula. The electrical potential energy is equal to negative Q E D. Maybe now we see why that we need to have a negative in this formula. I need to put a negative in front of the charge. And then I've got my, and this is coulombs by the way, and then I've got 400 newtons per coulomb, and then I've got a distance of 0.02 meters. A couple of things I want you to notice here. Maybe I'll calculate the number first and then we'll talk about it. We've got negative 1.28 times 10 to the negative 18th joules. Several things I want you to notice. First of all, the formula made a value that is negative. And again, that should make sense. If we're letting the proton go the way it wants to go, it's going to be losing potential energy. Next thing I want you to notice is what cancels here. I didn't do the best job of drawing the C because it kind of looks like it's in the denominator, but it's not. It cancels with this C, and what I end up with is newtons times meters, which is joules. So the units still work out the way that they did and they have all throughout this course.